and we've talked about one of the possibilities for what high mass stars can turn into when they die. That's neutron stars. Now we're going to talk about the other thing that high mass stars can turn into when they die, and that's black holes. But I would like to give you kind of a good idea of what's actually going on in black holes. That means we're going to need some background. So at the end of the 1800s, light was a really big deal. During the 1800s, we finally got a theoretical understanding of what light is, specifically that it was an electromagnetic wave carrying energy from one place to another, and we started getting the math and so on predicting how it would behave. Well, one of the big questions about how does light behave is, does light obey what we call Galilean relativity? Galilean relativity is the normal way that we have of figuring out how fast things are going compared to other things by just adding and subtracting their velocities. So, for example, let's say that we're cruising down I-15 going 70 miles per hour, and then we see a cop zip past us. As that cop passes us, we figure how, based on how fast he's moving compared to us, he's got to be going at least 30 miles per hour faster than us. So that means that compared to the road, the cop has to be going around 100 miles per hour. Okay, so we knew we were going 70, and that he was going 30 miles per hour faster than us, so 30 miles per hour compared to us, and therefore 70 plus 30 is 100. Hey, this is the normal way we add and subtract velocities to figure out how things are going compared to other things. Well, the question was, does light do the same thing? If light obeys Galilean relativity, then the speed of light that they would measure should be the normal speed of light, 3 times 10 to the 8th meters per second, plus the speed of the Earth. Hey, in that direction, it would appear that light was traveling faster because it's getting a boost from how the Earth is moving. They also measured the speed of light against the direction that the Earth was traveling. In that case, they had expected it to be 3 times 10 to the 8th meters per second minus the speed of the Earth. Okay, so it should be slower because it's going against the direction of the Earth, it should be going slower. Well, when they actually did this experiment, what they found is that there was no change to the speed of light. The speed of light was exactly the same in the direction the Earth was traveling as it was against the direction the Earth was traveling, as it was perpendicular to the way that the Earth was traveling. Okay, so what this means is that light does not obey Galilean relativity. This actually was really weird and not at all what anyone was expecting. There was a young physicist by the name of Albert Einstein who actually heard about this experiment and what it showed, and he included that into his theory of relativity. So this is what is known as the special theory of relativity, and it was published in 1905. Now, the special theory of relativity is based off of just 2 principles. The first one is that regardless of your speed or direction of motion, all observers always measure the speed of light to be the same. In other words, this is what Michelson and Morley had just discovered, that everybody always measures the speed of light to be the same. The second principle is that your description of physical reality is the same regardless of the constant velocity at which you move. So we're going to have to unpack this one a little bit more. So remember velocity. Velocity is both speed and direction. So a constant velocity is going to be the same speed in the same direction. So as long as you are traveling at a constant speed in a straight line, then your description of physical reality is going to be the same as anybody else's who is traveling at a straight line at constant speed. Now notice that it does not matter what speed that is. As long as it is constant, then your description of physical reality is going to be the same. For example, imagine an experiment where we throw a ball in the air. Just sitting here in the room, we throw a ball in the air. The ball goes up, it comes down, and that's it. I realize this is probably a very boring experiment, but we see the ball go up and come down because of gravity. Now, if you've ever been on an airplane in the middle of the flight, where you're just cruising in a straight line at constant speed, think about how it feels. Assuming you're not in the middle of turbulence, then it feels normal. There's no real difference. In that case, you could throw a ball in the air and it would go up and come back down, just like sitting here in the room. But you're definitely not traveling at the same speed. Here in the room, you're traveling at 0 compared to the Earth. In an airplane, you're going several hundred miles per hour compared to the Earth. But because it is a constant velocity, then in both cases, the experiments yield the exact same results. Now, the reason why we refer to this as a theory of relativity is because it is how things are moving compared to other things. It's all about comparisons. It's how things are relative one to the other. Now, the reason why we refer to it as special, this is the special theory of relativity, is because it does not include gravity. We do not include gravity in special relativity. Now, although the principles that go into the special theory of relativity are relatively simple, I hope that you can just accept them as they are, the consequences that we get because of them actually become very strange. One of these consequences is that as an object is moving very fast compared to you, so remember this is relative, if it's moving very fast compared to you, then we will actually see that its length is shortened in the direction of travel. Now, really quick, we need to define what very fast means. This is at least 10% of the speed of light. So 10% of the speed of light and faster, that's what we determine as very fast. So in other words, are you going to experience any of these effects in your daily life? Absolutely not. Nothing that we come in contact with in an everyday situation is going to be traveling that fast. And I think that is why these ideas are so very strange, is because we don't deal in things that move that fast. So, as an example of this idea of things shortening, here we have a train, and notice it is stopped at a red light, meaning it is not moving compared to us. When we go out and we measure the train, we measure that it is 17 meters long. So this train is 17 meters long. Now later, we have the exact same train, but in this case, it's going to be going very fast. And in this split second where it's right in front of us, we somehow come up with some experiment to measure it. Whatever experiment you can think of. Whatever clever idea you have to measure the length of this thing in that split second where it's directly in front of us, we actually go out and measure, and we find that instead of being 17 meters long, like it was when it was stopped, not moving compared to us, it is now only 12 meters long compared to us. So it is actually and physically shorter in the direction of travel. This is what is known as length contraction, and we've actually experimentally verified it. We see that this does actually happen. Another one of these bizarre consequences has to deal with time. Specifically, that an object is moving very fast compared to you, its time runs slow. Its seconds take more time than your seconds do. So imagine we had that train that was zipping past. As we watch the clock on the train telling us what time it is, for every 1 second that ticks by on that clock, several of our seconds will have ticked by. So their time is running slow compared to our time. This is what we call time dilation. So to dilate means to grow or expand. So their time is bigger, has expanded compared to our time. Again, I realize these ideas are very strange. However, the whole reason I bring this up is to show a couple of things. First, notice that space, lengths, and time are not rigid, meaning that depending on relative motion, they can actually change. Lengths got short, and time got bigger. The other thing is notice that they change together, that as the lengths got shorter, the time got bigger, meaning that somehow space and time are actually intermingled. Somehow space and time are related. This leads us to the idea of what we call space-time. Hopefully you've heard of space-time at some point before. And so we have the fabric of space-time is kind of how we refer to it. And this is going to help us understand lengths and time as we move forward. All right, here is our first lecture quiz question. You are in a spaceship traveling at 90% of the speed of light. In the ship with you is a meter stick. When you measure the meter stick, by how much is it contracted? A, 10%, B, 50%, C, 90%, or D, it isn't shortened at all. Go ahead and think about it, and we'll discuss in just a bit. All right, so what do you think? By how much is it contracted? The correct answer is D. It isn't shortened at all. Now, the reason for this is because the stick is moving with you, which means that it is not moving compared to you. And if it does not move compared to you, then there's no relative motion and nothing is weird. A meter stick that is traveling with you is always 1 meter long. Now, if I had said you are an observer on the Earth watching the spaceship zip past, how much is the meter stick on the spaceship shortened? Then yes, it would absolutely be shorter because it is moving compared to you. But because it's not compared to you, it is not shortened. So the correct answer is D.